All right. What a great crowd for this evening. Welcome. So my name is Denise Young. I'm the executive director of the Bell Museum, and the Bell Museum is thrilled to be part of the 2018 MIFA Public Lecture. As you may know, the Bell Museum is the official natural history museum of Minnesota, and it's right here at the University of Minnesota. We just opened a new facility 3 months ago. I'm hoping one day we see sunshine again like we had on this day. We moved right over to the St. Paul campus, and our mission is to ignite curiosity and wonder, explore our connections to nature and the universe, and create a better future for our evolving world. Our opening has been pretty fantastic. In 10 weeks, we've had over 70,000 people come through the doors. Many of those people have come to experience the new Whitney and Elizabeth Macmillan Planetarium. It's a 120-seat, fully digital, state-of-the-art planetarium that can take us on explorations of Earth, the stars, far reaches of the universe, and even inside of our own cells. I thought you might like, if you're not familiar with the Bell and the Whitney and Elizabeth Macmillan Planetarium, I thought you might like to know about it, so please come visit. We have shows daily, and they are on our website. The titles and descriptions are on our website. With the grand opening of the museum in mid-July, so now a lot of you know this rock star, Professor Larry Rudnick. The success of the Bell Museum really rests on the relationship we have with organizations and departments and programs such as MIFA and the School of Physics and Astronomy here at the U. The Bell is really poised to be a gateway to the sciences. I like to think of it as it's our potential and our goal to share the what of science and science research and the so what. We do that through exhibits, programs, planetarium shows, and special events. I do hope you'll come soon to visit us at the Bell Museum. We put brochures on the table right outside the door. Very easy to remember, we're open 7 days a week, 10 to 5 p.m., and we have many special events and programs. Now it's my pleasure to introduce Dr. Bob Gerritz, who is a professor here in MIFA.
So welcome to the Minnesota Institute for Astrophysics Fall Lecture. It's my very distinct pleasure to introduce this evening's speaker, Professor and Dark Matter Detective Priscilla B. Cushman. Prisca earned a BA in physics in philosophy and physics from Harvard University in 1976 and a PhD in physics from Rutgers University in 1985. Following a 3-year postdoctoral appointment at Rockefeller University, she spent 5 years as an assistant and associate professor of physics at Yale University. We managed to steal her away here in 1993, and she's been a professor in the School of Physics and Astronomy in our institute since 1993. Prisca is a fellow of both the American Association for the Advancement of Science and the American Physical Society. She's held leadership positions in a number of major collaborations in particle physics, and tonight she'll speak to us about the search for clues about the nature of the mysterious dark matter that pervades the universe. Prisca.
Thank you. Thanks. Welcome, everybody. So first I want to say that what I am not going to speak about tonight is how my experiment is going to discover dark matter. And that's because we've already discovered dark matter. So basically, to continue to stretch the metaphor, if you look at the evidence from the crime scene, it's clear that a shady dark matter syndicate has been responsible for the crime. So it's not that we're worried about whether it's dark matter. We actually want to know who is a member of that syndicate. And while we know that gravity is one of the weapons of choice, maybe there's some other weapons that they have in their arsenal. So, therefore, what my outline is for today is as follows. I'll talk a little bit about the crime scene and what we know. and then propose a very general hypothesis, which is that dark matter has mass, but it doesn't shine or reflect light, hence it's dark, and there's 5 times more of it than normal matter. I will then establish a prime suspect, something a little bit more specific than this very general hypothesis, and we're going to say that the dark matter particle also interacts via the weak force. By saying that, we then enable a worldwide search for this prime suspect. I'll talk a little bit about the police work. So I'll talk about the details of how we build an experiment and where we're going to look next. And I'll end by admitting to you that there's so far no sign of the prime suspect. So we're going to have to reopen the files on other suspects, but we won't stop searching for that prime suspect until we can't look anymore. So, told you I was going to stretch the metaphor here. So let's take a look at some of the clues from the crime scene. First of all, you know that if you're on a merry-go-round, the faster you go, the tighter you have to hold yourself in place, or you'll fly off the merry-go-round. And the same thing is true for stars that are circling the center of a galaxy, for example, our Milky Way. In order to keep the stars from flying apart, they have to hold on tight, and that's via gravity. And the amount of gravitational force that's holding them is proportional to the amount of mass. So basically what we found by looking at many of these galaxies and clusters of galaxies is that basically the stars are moving so fast that they should have flown apart eons ago if what we assume is that the gravity is only due to what we see. So here's the data. This is the velocity of the star on the y-axis and the distance it is away from the center of the galaxy. And if the gravity is just due to what we can see, then what we should have seen is that the velocities would follow this dotted curve. And instead, we see that the data shows that the stars are moving much, much faster. So this is the mystery of the missing matter. The only way that this works is to postulate that there is more matter out there. And not only is there a lot more than what we can see, but it's distributed at great distances from the center. Anyway, the second clue is the distortion of light. I mean, if we're going to have a lot more mass out there and therefore a lot more gravity, and if we know that gravity distorts and bends light, then we're going to get a lot more bending of light due to this dark matter. This is called gravitational lensing, and so what you see is a little cartoon. You have the light coming from a very distant blue galaxy, and on its way to our telescopes here on Earth, it has to pass through a lot of dark matter on the way. And so this picture shows you the fact that this galaxy, when you look back at that galaxy, which is shown in the blue, and in the foreground what you see are the clusters of galaxies, all of which are surrounded by this additional dark matter, you end up seeing shear in the images of the background galaxy, and even multiple images. So what you can do, of course, is look in all directions, look at these distortions, and what you find is that you can actually make a map of where all the dark matter should be in order to cause the lensing that you observe. And that's what this picture is here. This is a sort of iconic picture. The bullet cluster is actually a montage. It is observations from an X-ray satellite, that's in the pink, lensing studies in blue, superposed on this optical image. So the story that we can come up with this is that these are galaxies that for hundreds and thousands of years were merging, and the normal matter from the galaxies collided, and the hot gas is emitting the X-rays we see. On the other hand, the lensing studies show that the dark matter component of each of these pass through each other without effect. Well, it's telling us a lot about what dark matter is, or what it doesn't do. It doesn't feel the nuclear or the electromagnetic force. Yeah, I had a lot of fun with that. And I was actually debating until the last minute whether I should just turn off the audio, but be that as it may. What you do next is you propose an hypothesis, right? This is my hypothesis. This dark matter is a bunch of elementary particles that are created at the Big Bang. And because they have mass, and because there's so much of it, they are basically the engine of creating the structure we see in the universe. They basically create the gravitational wells into which the normal matter that will eventually ignite and create stars falls into. So we have to check that hypothesis, though. So why not reconstruct the crime scene starting from the initial conditions? So you want to come up with a simulation that will do that. And then what you want to do is see if that hypothesis accounts for the evidence you see. So what we're actually going to do is we're going to start with some initial conditions. To do that, we need a map of the dark matter density in the early universe. Then we will let it evolve, let the dark matter particles move under the influence of gravity for 13.7 billion years. And then at the same time, we'll be performing astronomical surveys of the distribution of galaxies and clusters of galaxies that we see now. And then we compare the two. Basically, have we, by doing this simulation, with the amount of dark matter we put into the simulation, do we come up with what we see today? Now, getting those initial conditions will take a few slides to tell you about, because I think I'll have to start by telling you a little bit about the history of the universe, irrespective of the dark matter. What you see here is a picture of the history of the universe, starting with the Big Bang on the left to present time on the right. Let's look a little bit in more detail at these early times. So this thing called inflation. Basically, what we're saying is that the universe started from a quantum fluctuation in the vacuum. And in 10 to the minus 35 seconds, the universe expanded to the size of a grapefruit, approximately. Now, it's not the size of the universe, which is so impressive here. It's the fact that it expanded so fast. And the way to get a handle on that is to realize that light takes about half a nanosecond to go across something that's the size of a grapefruit. Okay, a nanosecond is 10 to the minus 9 seconds. We're talking about 10 to the minus 35 seconds. What we're saying is that that universe has expanded 26 orders of magnitude faster than light. And that has consequences. It has consequences because those parts of the little baby universe that are expanding so fast cannot communicate to other regions in that universe. Because although, so let me take a moment, step back. You might be saying, wait a second, nothing expands fast, nothing can move faster than the speed of light. And you'd be right. Anything that's inside of space-time cannot move faster than light. Stars and planets and spaceships, they can't move faster than light. But that speed limit is ordained by space-time itself. There are no rules as to whether space-time can expand that fast. However, it's still true that within that space-time, one part of the cosmos has had no time to communicate with another. That means that if there is a density differential in that quantum singularity, then it cannot smooth itself out. And so the density pattern at the end mirrors those tiny quantum fluctuations in that singularity that started it all. Okay, that happened real fast. Now we can kind of rest for next couple minutes. Inflation ends. That's the thing that has powered this incredible expansion. However, the universe continues to expand because of all the energy pumped into it from inflation. But now it's also cooling. And so in those next couple minutes after the Big Bang, the particles are condensing out of this hot, dense quantum soup. So that's the dark matter. That's condensing out. The quarks neutrinos, any of the particles we know. And then as it gets cooler, those quarks can find each other and come together to make a proton. As it gets even cooler, those protons and neutrons that are composed of the quarks can form nuclei. So that'd be nuclei of hydrogen and helium. But they're not yet atoms. In fact, it takes about 400,000 years for the universe to cool enough to make neutral atoms. This is the point at which the electrons get bound to the atoms. Once that happens, something very interesting happens. Once the electrons are now bound to the atoms, the light, so over here, and this is before that happens, the light keeps scattering off these free electrons. So once the atoms become neutral, the light is free to stream through it. Basically, the universe becomes transparent. And of course, that light now can travel through this expanding universe and can be observed here on Earth billions of years later at our location in some other part of that expanding universe. So what I've done is just talk about this part here, right? Inflation, and then this light that is flowing through, this thing that as it flows through and the universe continues to expand, all of that light, that primordial light, becomes stretched. The wavelength gets longer, it has less energy, and it goes from being gamma rays and X-rays down into the microwave region. And that's what we call the cosmic microwave background. And the point here is, we're still trying to get to those initial conditions, if you remember. These patterns of density that were first encoded in the quantum singularity are now frozen across and imprinted on the light that we receive. Sometimes, actually, I put the second one in because this is sort of misleading. People kind of think, well, I'm here, so I should look back to wherever the Big Bang was. But the Big Bang is actually all around us. We started in this inflationary scheme, and the better way to look at it is wherever you are in the universe, but for example for us here, we look backwards in time in every direction to these initial conditions, which we call the cosmic microwave background. Okay, that was a lot, and it was all in order to get to our initial conditions in this check hypothesis part of my slide. So our initial conditions, therefore, is a snapshot of the oldest light in the universe, imprinted on the sky when the universe was 400,000 years old. So tiny differences in the frequency of that microwave radiation. So we have satellites, with microwave detectors, and they're looking in all parts of the sky, and they're measuring these very, very tiny differences in frequency. And what that is doing is allowing us to find places of different density. So in a place like this, there's coded in blue, meaning that it's a little bit less dense, or a place like this where there's more matter. So what we're going to do is run a simulation. We're going to arrange all the dark matter particles according to that initial density map. Then we're going to code in the physics of gravity and the laws of motion, and we're going to press the button and let the computer do the work and track all of these particles over 13.7 billion years. So what I have here is one of these simulations. The fact that everything seems to be moving right now is actually because sort of the camera angle is shifting around to look at what you're seeing. What you're seeing is the density of the dark matter. And the initial conditions were set to match that density map I showed you. And as time goes on, everywhere there's an overdensity, it pulls in the other particles around it and becomes even more dense. Eventually, these really dense regions will bring in enough other matter that it will ignite and create stars. And then those regions of overdensity will also collect into galaxies and clusters of galaxies. Just a few other, as you're watching this, you'll notice that the time since the Big Bang is here, so we're at 1 billion at this point. You'll also notice that the time scale is 500 kiloparsecs. It's about, I'm not sure, that's 780 or so kiloparsecs to the next galaxy from where we are. In our galaxy, the visible part of the galaxy is something like 30 kiloparsecs across. So we're basically looking here at a simulation of how our dark matter cloud gets formed. And you can see that at the very center of the Milky Way is the densest part. It's the densest part of the normal matter that we pull in, but it's also the densest part of the dark matter. Let's see what else to say here. Actually, not sure how to make it stop. It's got to get up to 13.7, I think. But another thing to notice, actually, that I find interesting and people don't realize is, gravity doesn't just go boom like that, right? Gravity pulls stuff, and it gets some momentum. And then it sometimes slingshots around and comes back. So a lot of that motion you're seeing is still just gravity. We'll go on. Okay, so we got to get to the prime suspect here. I just told you why there's evidence for dark matter, but I haven't told you much about the kind of dark matter we're looking for, which is a weakly interacting massive particle. Now, what I've written here are the 4 fundamental forces that we know about: gravity, electromagnetism, the strong force, and the weak force. So what do we know so far about dark matter? Well, I've just given you a lot of evidence that dark matter interacts gravitationally. Therefore, it has mass. We know it does not interact electromagnetically. It neither shines nor scatters light. It also does not interact via the strong force, because if it were interacting with all of our nuclei in our body, and if it were interacting with the Earth, we'd all be dead by now. But nothing forbids it to interact with a weak force. But we also have a positive motivation for looking for something which might interact with a weak force. So 2 objects that have mass do not come to each other and then annihilate. But if the weak force is there, then yes, there would be such a thing as a WIMP particle and an anti-WIMP particle. And when they found each other, they would annihilate and turn into energy. So let's imagine that in the early universe, this is happening all the time. It's hot, it's dense. All these WIMP and anti-WIMP particles are really close to each other, and they're basically annihilating and reducing the number of WIMPs that exist. Now, of course, as the universe expands and cools, these WIMPs and anti-WIMPs get further apart, and so the annihilation rate begins to slow as the universe cools and expands. Finally, at something we call freezeout, the WIMPs are so far apart they can't find each other to annihilate anymore, and however many are left is what we have today. And we call that the relic density. Well, the rate of annihilation depends on the interaction strength. We might call it a cross-section or something like that. But that just means that the stronger the interaction is, the more the WIMPs are annihilated when they meet each other, meaning that fewer are left at freeze-out. So what we find is that if we assume that the interaction strength or the annihilation rate is that which is characteristic of the weak force, then we end up calculating, we get the dark matter abundance that we measure today. And when this was first calculated and worked out, people called it the WIMP miracle. And in fact, it really did generate this manhunt for the WIMP that has been happening over the last 2 decades. There's actually some further motivation. We're going back to our stretched metaphor. Imagine that you had a cold case. You had this thing called the schoolhouse murders. because we have Professor Plum as my prime suspect. So let's just imagine that there was an unsolved murder and the MO fits that of the prime suspect. We have two crime scenes pointing to the same perp. It's circumstantial evidence, but it might make you think twice about this wimp. So to take it to the physics side of things, we have a long-standing problem in particle physics regarding the unification of the fundamental forces. And it turns out it can be addressed by proposing a family of new particles. And that theory is called supersymmetry. The masses of those particles are actually predicted to be within the discovery range of the Large Hadron Collider. This is the collider over in Switzerland, operated by CERN. And that whole family of particles, they'd be heavy, they would have interactions, and they would then decay and interact down to the lightest one, beyond which it can't go any further, and it would be neutral, and it's a perfect candidate for a WIMP. But I have to admit that all the evidence I've given you so far is circumstantial. However, it's very compelling because once you have a prime suspect and you have an MO, you can actually build an experiment. You can't build an experiment on Earth to measure gravitational interactions, at least not of this type. But you can if what you're looking for is a weakly interacting particle. And you can also you can make them. I mean, if these interact with a weak force, we can create parent particles using the strong force at CERN, and we can find the decay particles and detect them at the Large Hadron Collider. Now, I do want to relate this a little bit to another famous particle that you may have heard of, the Higgs particle. That was predicted in 1964 and then found at CERN in 2012. It was amazing because it had been predicted so much earlier, but it really was the linchpin of the Standard Model. In fact, people would have been far more disturbed if they hadn't found it. It's fundamental to understanding the Standard Model of physics. But these WIMPs, they just came out of nowhere. They came from the fact that we made these astrophysical observations, but they were not predicted from the Standard Model. That means if we can understand their properties, we're going to be able to find a way to extend the Standard Model, to incorporate them, and we'll learn a lot more physics. Okay, so now I'm going to kind of change gears. I'm talking about how we build one of these detectors. And the first thing I need you to remember is that dark matter is everywhere. As right now in this room, it's streaming through you and me, right through the Earth, through the other side. We are sitting here on the edge of the Milky Way, but the dark matter cloud, sometimes called a halo, extends far beyond the luminous matter and, of course, inside as well. But that means that as our solar system moves around the galaxy, we're always being buffeted by this stream of dark matter particles. In fact, from our frame of reference, you could imagine it's sort of like a WIMP wind that we feel. So here's another picture of the same thing. What I've got here is the proper orientation of our solar system in Earth's orbit relative to the motion of the entire solar system around the Milky Way. And if we want to try to figure out how to design a detector, we're going to need both astrophysics and particle physics. So for the astrophysics, we need to know the distribution of dark matter in our local neighborhood. We model it as an isothermal spherical cloud, use some sort of velocity distribution like Maxwell-Boltzmann. It has an energy density of 0.3 giga-electron volts per cubic centimeter and a speed relative to the Earth, or our speed relative to it, of about 220 kilometers per second. For the particle physics part, we need to know how these things will interact with our detector. So if they're a WIMP, which means they're weakly interacting, they will scatter off the nuclei in our targets. And it will make that nucleus recoil into the material, and we can then calculate the rate of those interactions and how much energy that recoil deposits into our detector. But you might ask yourself, I just told you that there's dark matter in this room, it's streaming through us at all times. I also told you that there's a stiff wind of 220 kilometers a second and an energy density of 300,000 electron volts in every cubic centimeter of space, so why don't we just see it all the time? And the reason is not because the weak force is intrinsically weak, because it actually isn't. It's related to the electromagnetic force, and it has a rather high innate strength, but it is short range. So dark matter needs to get within 10 to the minus 18 meters of the nucleus in order to interact. And so only 1 in 10 trillion gets that close. This picture will come back again. You can see we have a nucleus and we have a cloud of electrons. Because of the mass of the WIMP, it preferentially scatters from a nucleus, whereas lighter background, generally particles, gammas and betas and everything, they scatter off the electrons. We'll come back to that in a moment. I do have to say that even this picture is misleading, because that nucleus is just not to scale compared to where the electrons are. It's nice because you kind of have that view through the crystal, right? But if you really want a better scale, imagine that the nucleus is the size of a grape. That would mean that the electrons are basically forming the Viking Stadium outer shell. Basically, we're all empty space, mostly. Held apart, our atoms are held apart by the force field, and mostly electromagnetism. The weak force just goes right through, or the WIMPs do, because they interact with the short scale force, short range force. Okay, so now I'm going to talk about my experiment, which is the cryogenic dark matter search, or CTMS. And we are going to record the position, the energy, the pulse shape of the vibration and the charge released every time a WIMP strikes one of our nuclei in the target. So here we have a picture of what's going on. We have actually I have one here. This is, I'm going to pass this around. This is a prototype detector, but it gives you an idea of the size of one of our detectors. It kind of looks like about the size of a hockey puck, made of germanium or silicon. And when a particle comes in, it strikes a nucleus, that recoils and produces both vibration, or heat, or phonons, which is basically a fancy word for quantizing those vibrations. It also produces electron hole pairs, and under a voltage differential between the top and the bottom of our crystal, we can pull those electron hole pairs apart, and electrodes will measure the ionization energy as well. So I'll just maybe, okay. You can just be passing this around. Now, to make such detectors requires techniques from the semiconductor industry. We have to make a monocrystal, basically grow it in a furnace by the Joukowsky method. So here's a picture of a seed crystal being pulled slowly in a very hot furnace. What we get at the end of that is something called a boule that looks like this. And then we cut it into these sections and polish them and make these substrates of germanium or silicon. And then we go to a clean room. Metal films are deposited on the top and bottom of those substrates by photolithography. And basically what we're doing on that surface is putting a bunch of thermometers on there. So come back here. These are going to turn into detectors. The pattern that you see on the detector that you're passing around, right, is not exactly the pattern that I will show you here. It was, we tried a lot of different patterns. But what we're patterning onto the surface are thermometers, but very special kinds of thermometers. We want to measure, remember, that vibration or that heat from that one nucleus being bumped out of place. They're called transition edge sensors. They're about 1/10 of the width of a human hair. And they're and there's about 1,400 which are arranged in 6 channels on each side. So in fact, the detector has divisions which allow us to tell if a particle hit here or here or here. But each of these divisions has many, many of these thermometers on it. Now, for those of you who are kind of tech inclined, these transition edge sensors are held at close to their superconducting critical temperature. So these are thin pieces of tungsten, and they go between superconducting and normal. Something that's superconducting is something which, under the influence of a current, has no resistance. A current can move forever. But the moment it gets a little bit warmer, the resistance sets in, and it's very sharp. So what we're doing here is figuring out a way to make an extremely sensitive thermometer. It's basically any small amount of heat will end up in a very large change in the resistance. So this is what we actually have 2 technologies we use. This is one of the technologies, and you can see the different channels here. If you were to look carefully at this one part, you'd see these sort of blue beads coming along this line. Each of those is the TES is actually inside here. Here's this transition edge sensor, and around the outside are aluminum fins that help collect the phonons, or the vibrations. And at the same time, interleaved between them, we have electrodes where we collect the charge. So each of these, so we've got 6 and 6, that's 12 channels of phonons and 12 channels of ionization. And each of those channels will give us a pulse if a particle interacts with that. I've shown you, these are the phonon pulses. The ionization pulses are not milliseconds, but much, much shorter. So any of these detectors will actually have 12 times 2 different pulses coming out every time an event occurs. Then we stack them into what we call a tower. So there's 6 here, and all the electronics that we need for readout are also on this same tower. It gets inserted deep into a cryostat because we need to keep this supercooled at the critical temperature. The readout cables then come out here. Another picture might be easier. Okay, so here is this cryostat showing one tower inserted within it. The cables come out the top and through the electronics stem and are read out. And a helium dilution refrigerator here via a cold stem keeps this set of nested copper cans cold enough to maintain that transition temperature. We call this the cryostat, the fridge, cold stem. Just a comment that what we're doing is we are keeping the temperature inside this cryostat at 30 millikelvin above absolute zero. And if you want to think about what that means, we just talked about the cosmic microwave background. This bath of cosmic microwaves in interstellar space is basically keeping the temperature a toasty 2.7 degrees above absolute zero. This is 90 times colder than interstellar space. Then we have to surround the cryostat by layers of shielding to reduce the flux from the environmental radiation. So we don't have to go into great detail. There's water, there's lead, there's polyethylene. However, in order to understand why we need the shielding, I thought we could all take a little pop quiz now. I'm going to need 3 brave souls to raise their hand in a moment to guess. You don't have to know the answer, but I'd like you to try to guess. Why why this is so hard to get rid of the radioactive background. And the way I'm going to ask that question is, how much radiation is your body right now putting out and irradiating the person next to you? In becquerel. We call that becquerel, but it's just how many decays a second is your body putting out, and where does it come from? So 3 people want to just guess? Guess? How many? Or shout it out. Yeah.
I have to say a quarter, and it's probably because of some of the potassium isotopes in our body.
You are absolutely right about the potassium. And potassium is something that we have naturally in our body, and of that potassium, a certain percentage of that is radioactive, and it's potassium-40. In fact, let's see, is there some other material that's in your body that you could imagine might also be radioactive?
What kind of radiation are you talking about?
Wow, I'll mention that in a moment. Now I'm talking decays, stuff, radiation, just stuff that comes out because there's a natural decay. So carbon, we're all made of carbon, and there's carbon-14. So that would have been the other one. And the amount is 4,000 from the carbon-14 and another 4,000 decays every second from the potassium-40. If you want to break that down into the particles themselves that are coming out, that's about 8,000 neutrinos, 8,000 electrons, and 400 gamma rays coming out of you every second. This is going to overwhelm our detectors. So obviously we're not going to want people right next to our detectors, but let's look at other backgrounds. So for example, we all know it's not a great thing if you've got radon in your background, in your basement. But do you know how many radon atoms, this gas of radon that will be radioactive, escape from the ground per square meter per second? Anyone want to guess? Shout out a number. 10? A million?
I have to say a trillion to a quadrillion.
Wow, yes. Now that is a lot. And in fact, thank you for being so brave. The rest of you should take a lesson from her. It's actually 7,000 atoms of radon just coming out right now, well, probably more from this concrete, per square meter per second. And I'll just give you this one. Plutonium, how many plutonium atoms you find? This is closer to a gazillion. This is tens of millions. And it's caused, actually, because the soil has 1 to 3 milligrams of uranium in every kilogram of soil. And the cosmic rays that are raining down on us all the time, not dark matter, just regular old cosmic rays, transmute that uranium to plutonium. So reducing backgrounds is like one of the hardest and the most important part of any dark matter experiment. So what you'll find is that every dark matter experiment goes deep underground, and that's to escape these cosmic rays. So we're going to be building, this is Sudan in northern Minnesota. I don't know if some of you ever went on a tour up there. That's where we used to have our experiment. And we're moving to Snow Lab, and we're ending up, instead of being, a muon per centimeter squared per second, we're down to a few muons per year per centimeter squared. So it makes a big difference going underground. In addition, we have to use that additional shielding to get rid of the radon and also the trace radioactivity from the cavern rock. I said radon twice. And all the shielding has to be, you can't just go and put shielding that you've made from stuff that you mine and put it around, because you're just going to bring some more background into place. So you have to get very, very special shielding it's very, very radio pure. Now, I'll just give you a little bit of history of CTMS. We started in 1998 at a very shallow site at Stanford, actually a location where they used to have one of their accelerators. And moved in 2002 down to Sudan, so deeper at Sudan. So from 2003 to 2009, we called ourselves CTMS 2. And then we made bigger and better detectors, and so from 2009 to 2014, we called ourselves Super CTMS. And then, now, what we're hoping for is another decade of looking for dark matter at the Snow Lab in Canada. Each time that we go deeper, we can basically have more exposure before we become background limited. In other words, exposure is just how much stuff, how many kilograms, for how long was it exposed. So we went from 30 kilogram days to a kilogram year to 6 kilogram years. And here I didn't write down how much, but we can go up to 180 detectors and before we ever get limited by the cosmic rays of the background there. And this is a picture of Snow Lab. It's 2 kilometers deep. It's a working mine, actually. It's a nickel and molybdenum mine operated by Vale, which is the mining company. And all of the mining is over here, but there is a laboratory underground called Snow Lab, and it's named after the Sudbury Neutrino Observatory. So Art MacDonald received a Nobel Prize a number of years ago for the work at that neutrino observatory, which is located here. And our experiment is going to be built in this position here. This is actually a computer model of how we're building. Right now, we're building this up for our experiment. Here's this cryostat in which we would put the detectors. We would then, this then comes down into this large shield, which is finally surrounded by a water tank. The detectors are actually put into this cryostat here in the clean room, which has its own radon mitigation plant to make sure that there's no radon in that clean room when we install the detectors. And then I had install a little Google person from Google Map, because what I want you to do is imagine that you're standing there, and actually the picture's taken here at me standing there about 2 weeks ago, and that's that. So we really are getting this thing going. We've got most of the infrastructure in place, and we've surveyed the area, and we'll be installing next fall and commissioning in 2020. Okay, so next step, I want to show you some plots, but I need to prepare you so you understand how we plot our results. On the y-axis, we have how many WIMPs there are times the interaction strength. On this axis, we have the mass. When we look at something for a certain exposure, a certain number of kilograms for a certain amount of time, and don't see anything, we can set a limit. So what this says is that we haven't seen anything up to this point. If there are fewer WIMPs, so they just never interacted yet, that's okay. But above this line, we've excluded those properties of WIMPs. So if we go for longer exposure, if we get better background rejection, and still don't see anything, then our line will be lower down. And it will cover the region that we're sensitive to for the masses of a WIMP. So that's the other thing I need to point out here. We're talking about an elementary particle, but we're talking about an elementary particle without additional elementary particles inside that has a huge mass. I mean, it can have the mass of a germanium nucleus, but not made of protons and neutrons, but just on its own. And so this is sort of the range we look at, from the mass of a proton to the mass of a uranium nucleus, what we're sensitive to. Now, if we actually got some detected, we would be able then to know what its mass is, because we've seen some, and how many there are. So whenever you see a line like this, that's a limit. Whenever you see a contour, it means someone thought they saw something. Now, actually, our lines don't look like straight across lines. They look more like this. And that's because on the low energy side, we hit our threshold or we hit noise, so we get less and less sensitive as we move to the left. On the right side, it has more to do with being able to calibrate things at such high energies. And in the middle, there's sort of a sweet spot. They all look like this, sort of, and where that is depends a little bit on the target. If you have a lighter target, you kind of match the weight of the target to the mass of the WIMP. It's more kinematically favorable for if your target is about the mass of the WIMP that actually interacts with it. It gives you the most recoil. Okay, so now this has a lot of stuff in it. But what you can see are these limits with this kind of curve that you saw. You can also see some contours. That means people thought they saw something. And these are just the names of many different experiments who have put limits or contours. I do want to mention this here. This is called the neutrino floor. It's basically where you start getting scattering from the lightest mass, the lightest WIMP that we already know about. So a weakly interacting massive particle we know about, but it's not very massive, is a neutrino. And neutrinos are produced from the sun. They're produced from supernova. There's a diffuse background all the time. And so if we get to this point, we're going to get confused between whether we're seeing a dark matter particle or just seeing a neutrino. So we sort of think of that as the end of where we're going to look. Beyond that, we're no longer a WIMP detector, we're a neutrino detector. This is great for the funding agencies, because they kind of get sick of, look, you're just going to build another bigger device for look for something that you haven't yet seen. And we say, no, but there's an end. When we get to here, we'll stop, we promise. Okay, this is 2014, and the U.S., this Department of Energy and National Science Foundation, they're the main funding agencies, decided that in order to save resources, they were going to have a competition and only choose 2 detectors to move forward to the next generation. And those 2 detectors were ourselves, Super CTMS, and another detector called Lux Zeppelin. Now you can see that basically it was a complementary strategy. Super CTMS, these detectors, we can actually go to lower and lower thresholds. So we can move into this region here by looking at tinier and tinier amounts of energy. Whereas the liquid xenon experiments can just, because they're easy to scale up, they just can get bigger and bigger. And by brute force, push their way down. And so therefore I have to mention something about our competitors. It looks similar. You can kind of see you've got all of this shielding you need. And in the middle, in the sweet spot, that's where the detector is. In this case, it's 7 tons of liquid xenon. Again, any dark matter experiment has to go underground. This one is at the Sanford Underground Research Facility, or SURF, in Leeds, South Dakota. I will tell you a little bit of how it works. It's sort of the same thing. You have a big target, and you're waiting for a WIMP to interact with the nucleus and bump it. So here, when the particle bumps an atom in liquid xenon, it produces light. So we're not talking about vibrations anymore, we're talking about light. And on the top and bottom, you have photodetectors, which see that light. And so you get a little blip if you're just looking at a function of time, and we call that S1, scintillation light 1. In addition to producing light, it also produces electrons, and there's a field, an electric field, and so again, you drift the electrons across under the influence of the field until they hit an interface between the liquid and the gas phase. At that point, that electron actually sends out a spark of light also. And that light is, again, seen by these photodetectors, and that's S2. So you notice that you get 3D position information these individual detectors tell in X and Y where it hit, but also the amount of time it takes to drift is short if the interaction occurs near this surface, and long if it occurs down here. And by measuring delta t, you also figure out the z position of the interaction. So anyway, we're actually looking not just in the US, but worldwide. So I guess the analogy would be Interpol. This is actually a picture from 2014 because the limits I showed you were from 2014. So if these are posted online and you're interested enough, you can go look at all the different, of course, each of these is at an underground lab, right? And the names of the different kinds. There's cryogenic techniques like we use. There's noble liquids like LZ uses. And there's also solid scintillators. Okay, 2018, what's happening? Now, you won't remember perhaps what you saw before, but this is what was in 2014. This limit was there, one of our limits. And while we've been building our experiment, and while LZ has been building their experiment, progress has not stopped in the rest of the world, and the limits are getting better. And most of those contours you saw are gone. People have decided either they think it's a background, or they just appreciate the fact that these limits have gone far past those contours. Those contours couldn't be right. Now, those contours are coming from seeing one or two events, right? So you have to, no one was making a big statement that they had discovered dark matter in those contours, except one group called DAMA. And I need to take a moment to talk about DAMA. This is the Italian collaboration who has declared that they have detected dark matter for the last 20 years, and no one's paying attention to them. And anyway, let me tell you what they do, because it is interesting. They have an array of sodium iodide crystals, 25 crystals, each is a 9.5 kilograms, and they have it in an array like this. It's located, of course, underground in the Gran Sasso lab, which is, so there's a mountain here. You can actually drive in a tunnel under the mountain, and the laboratory is to the side of that drive-in tunnel. They are an annual modulation experiment. I haven't really talked about that, but instead of just counting the number of recoils, they look for a small annual modulation on top of a large background. Let me remind you that when it's December, the Earth is actually moving June, December and June, you're either moving with or against the WIMP wind. And so this fact that you are sometimes increasing the average velocity and sometimes decreasing the average kinetic energy with which those WIMPs strike your detector means you should be able to see a difference in the energy and number of particles above your threshold. And here's their data, and it's very impressive. This is a 12.9 sigma modulation. However, from that previous, if it's WIMPs, we should have also seen it, and we didn't. So there's a real contradiction here. Nobody. I don't know if it's still working out. Nobody disagrees that there's a modulation, but we don't know what it is. So very recently, there's finally a worldwide effort to check DAMA with another experiment. It's called SABRE, and they have sodium iodide in the same lab and sodium iodide in the southern hemisphere as a way to see the, so basically one of the backgrounds that this, I think I'm losing my mic. One of the ways in which, can you hear me all right? Is this still working? Is it cutting out once in a while, or? Okay, I'll just keep going till it really cuts out. Basically, in the northern hemisphere and in the southern hemisphere, we know that the cosmic ray muons have a seasonal variation also. And if somehow they aren't getting rid of that background, then maybe their modulation is due to the cosmic rays and nothing else. In that case, finding a modulation in the southern hemisphere where that flux is actually in the opposite, the opposite phase, will help clear that up. And there's a lot of other people getting into the act as well. I want to say the reason that this took long, really a long time, is twofold. One is a lose-lose situation. It takes a lot of money to build and then operate a long-term experiment like this. What happens? Say you prove that they're right. Well, then they get the credit for seeing it first. Say you prove it's wrong. Well, nobody believed them anyway. So it's not, it took a long time for people to convince the funding agencies. There's a second reason it was hard. It's because DAMA had a contract with the crystal making company, which is really the only one you go to, and they wouldn't allow anyone else to make pure crystals. Okay, so I have just a few more slides. The reason that DAMA was so interesting when it first came up, so if you imagine that you didn't have all these limits, you just had this contour, everyone was really excited about it, especially because it was right in the sweet spot of where we predicted that supersymmetry would say that this WIMP particle would be. It was perfect with respect to what theory said. In fact, we used to plot 15 years ago or so, this is how we would make our plots. One, we would never bother plotting below a WIMP mass of about 10. And we always plotted these gray areas, which were the newest theoretical model for where the WIMP was. So what we really thought would happen is as we moved down in sensitivity, somewhere in this region, we would find this weakly interacting particle. Well, fast forward to now, and we just keep marching down there with no sign of this prime suspect. And so supersymmetry also has not been found at the Large Hadron Collider. People have been searching for it. They haven't found it. There's still some space left to try to make it work, but it's harder and harder. Direct detection has now eliminated much of the region predicted by theory. And something I didn't talk about at all is there's also no clear evidence of course there's with gravity, but of a weakly interacting particle from astrophysics. I told you that these WIMP and anti-WIMP particles couldn't find each other once the universe had expanded. That's not completely true. I lied a little bit because they then in places that are, centers of galaxies, wherever there's a density, overdensity of these particles, they can again find each other and annihilate, and they would then have a signature from that annihilation, and people are looking for that and haven't seen it. So we have to broaden the search. I think I don't have enough time to go in great detail, but just saying that the community is very interested in other theories that push to lower mass dark matter. One of them is this thing called the dark sector, which means that the dark matter particles are interacting with completely different forces, but they can be seen in normal matter because there is, first they mix with a mediator particle. Anyway, the main point here is all these new theories say that these particles are much lighter than what we were looking for before. And they could actually cause these electron recoils just like our background. So we have to look at everything. So LZ can continue to hunt for the prime suspect by brute force, but we need to be nimble to explore a whole range of new suspects because what we're looking for is no longer really what we used to call a WIMP. We're looking at much lower masses. So our first payload is 4 towers with 2 different technologies and 2 different target materials. Later on we can talk about what, how they are optimized. But our limits are all with these 4 One thing I want to mention is with this first 4-tower payload, so this gray is where the limits are now, in 2021, we should already be getting down to these limits. And by 2026, the larger picture might look like this. One, we hopefully will begin to address whether these contours by Dama really should be there or not. By 2026, if we don't see anything, the limits will look much more like this. Super CTMS will have been pushing down on the not necessarily WIMPs, low mass, dark matter, whatever it is, section. And the noble liquid experiments will be pushing down on whether the prime suspect is a WIMP. If we still don't see anything, there's even a proposed generation 3 called Darwin. At that point, the whole world has to be on one experiment. It's just too expensive. And so this would be experiment Darwin, and everyone would join it. Of course, it might not be like that. It might be like this. And if that happens, of course, we're not going to do a Gen 3 down here. But I'm pretty much finished. Let me put my summary up here. There's been an extraordinary progress over the last 2 decades in this direct detection technology. This worldwide effort has improved the sensitivity by 6 orders of magnitude. And we've been guided by a very well-motivated candidate called the WIMP. But it's been a lot harder than we thought. We still have no trace of the WIMP in our detectors. We don't know how to interpret Dama. No trace of supersymmetry has been found at the LHC, and no astrophysical evidence other than gravity, which I started this lecture with. So we are reaching an intrinsic limit to the WIMP search based on how well we can avoid this trace radioactivity in other backgrounds, and this, one of the backgrounds now is this neutrino scattering. How big we can make our detectors and how much money, let's be honest, that we're willing to spend. But there still is some room for the WIMP to be found before we hit that limit. And CTMS, anyway, is turning our attention to look for other models of dark matter, and the technology is becoming much more diverse. And that's the end of my talk. So there are two major U.S. agencies. You know how much is it? The department? Repeat the question. I think the question is who and how much gives us money. And so the agencies are the Office of Science in the Department of Energy and a National Science Foundation. Our experiment is about $20 million over, to build it. And then there's, I don't remember what LZ, it's a good deal more, 100 million. And then the other experiments in other countries are from their agencies. That's a very good question. And in fact, there's a group of people who are looking at something called MOND, which is how can we change gravity in such a way that, that maybe that's the thing. We just don't understand gravity well enough. But that's very hard to do, and they have not been successful in finding a theory of a new way that gravity works that's also consistent with all the experiments we've done on how gravity works. And in fact, I would have to say also that inventing a new particle is not a crazy thing to do. I mean, it's as far as an Occam's razor type of a thing, it's actually the simplest way to take the next step, is just say, oh, there must be another particle that we just didn't know about yet. Because we in particle physics think that, matter is made of particles and forces are made of particles. So it's not a stretch to invent new particles, but to try to detect them and understand them, that's been hard. Well, so that's a very good question. Okay, the question was, why can't, we said, okay, maybe it interacts via the weak force, but why not with the strong force? Well, the strong force, of course, is the nuclear force, right? And so if these dark matter particles were interacting with the strong force, we would see evidence of that. Probably the best evidence is that, do you remember that picture I had of those 2 colliding galaxies in the bullet cluster, right? And what we saw was that the dark matter did not get stuck in the middle. It moved right through. And if it were interacting with a strong interaction, it would start interacting with all the other normal matter that's there with their nuclei, and it would create tons, not just of X-rays, but lots of other particles and gamma particles and lots of stuff. So we actually know that's excluded. No. I can tell I can tell you that when I say something like every galaxy has about 5 times more dark matter, that is not completely true. There are variations. There are bands of dark matter. There's actually a galaxy or two that's just dark matter. And so are you talking about maybe a galaxy that's rather, doesn't have as much dark matter as
I don't know.
Okay. Well, there are other people here who might be able to answer that.
I know nothing about this. You, Larry?
I don't know if she's here.
We're in the dark.
But if you came up here afterwards, you'd probably get a collection of people who would be happy to just argue about that till we figured out.
Prisca, we got someone on back here. Been waiting.
Is our dark matter cloud still condensing, and to what degree?
So certainly there's movement in the cloud, right? And knowing whether our particular one is, we know their structure, things called cusps. We know that it's still moving under the influence of gravity, and if there's parts of it that have some original motion, for example, they will continue that. For our own Milky Way, it's not condensing in the sense that it's all getting squished together, but there's certainly motion. And when I talk about modeling our dark matter cloud around us, we include the fact that it's not just all still and stationary. There's motion and velocity in the parts that are there. But as an overall condensing, no.
It's no longer? It's no longer condensing?
Right. It's no longer getting shrinking, right? But it's certainly, there's motion. If you remember that, the simulation I showed, all those orbits, if you like, of parts of the dark matter moving, that's still happening.
We got someone in back here for a question.
Okay, so I was wondering, given the rate of interaction with, given the rate of dark matter's interaction with atoms, as you stated previously, what would be the frequency of detection in like a single detector? Like how often should you be seeing these?
Oh, okay. So, of course, as our limits go down, our answer changes, right? But with our best guess now, our detector, if we're right at the limit now of being ready to see them, we should see a couple a year, okay, in about 30 kilograms of material.
Question right here.
If dark matter interacts gravitationally, could we expect to see objects comprised entirely of dark matter somewhere?
There is supposedly this almost entirely dark matter galaxy. It can happen. It depends, that we have a huge universe and we have lots of fluctuations, right? And what we're doing is saying that the dark matter is pulling in the normal matter with it. But if you have to have a fluctuation in a certain part of space or there was some dynamics that went around, you could imagine that you'd have a place where you'd have 10 times as much dark matter as you do normal matter. Could happen.
Okay, we have a question right here, Prisca.
Okay.
Right up here.
What about searches for types of particles other than WIMPs? For instance, I've read about there's been a search for axions, which would be produced by photons shining through a magnetic field, and that's another potential dark matter candidate.
Right, so I kind of oversimplified, as one does for these talks, and said that the U.S. was funding two. Actually, I was correct. I said it's funding 2 WIMP experiments. It's also funding a 3rd dark matter experiment looking for axions, the University of Washington. And that is absolutely a place People are looking for really tiny particles, and they also have, in the same way that the schoolhouse murders were a motivation for us to look for WIMPs because we had an unsolved problem that the WIMP could solve that didn't have to do with dark matter. Just great, we killed two birds with one stone. There's also, for the axions, solves a problem in symmetry that has been a long-standing problem. So axions and WIMPs definitely are the two, but an axion experiment can't look for a WIMP, and a WIMP experiment can't look for an axion. They're just very different MOs, since I'm stretching this metaphor, and the detectors look very different as well. But we haven't seen either.
Well, let's thank our speaker.